Good day to you. This is Anagalactic, and you can see we have this is experimental. In the prior two lectures, we covered basic geometry, the point, line, and circle. We have been able to determine that the correct position of the number 1 is as a two-component one, which would be 1 over 1. 1 over 1 is the relationship number that defines the circumference of the circle. When you do that, you can mathematically explore what you just did, and you'll see here the first chicken scratch is an identity. The second chicken scratch is ultimately profound because it changes our number system to a unity-based system of two-component numbers. E to the I tau power equals 1. Tau was invented in the 21st century, and as there is a pi day every year, there is also a tau day every year, because tau is the correct number. Because you'll see the glyph looks exactly like pi without one of its legs. So tau is a very well chosen symbol, but it should have been E if Euler had gotten his way. And since E was then an open variable, Euler suggested it for the natural logarithm, and that did stick. So that's interesting that Euler tried to use the variable E for two suggestions, one of which was rejected. Well, it shouldn't have been. The grid, the Cartesian grid, is a two-componentization of extrinsic geometric space. It makes square space. If you extend that to 3D, it's cubic, and if you extend it to spacetime, it's hypercubic. So that's a very interesting extrinsic geometry. What you're looking at here is a non-extrinsic, non-Euclidean geometry. Euclid discovered the number line. That's why he's immortal. He discovered the number line. The closure to Euclid's work was only accomplished in the second half of the 20th century by John Horton Conway, one of my teachers. Surreal binary number tree, now admitted by all mathematicians to be the definition of a number. He got it. He closed Cantor's insane work. He basically rescued Cantor from the insane asylum. In order to justify Cantor's effort, which was doomed to failure, why? This is critical. Why was Cantor's work doomed to failure? Because he began with a contradiction. What Cantor tried to do was dequantize the Euclidean line. In other words, he tried to denumerate the numerical overlay on Euclid's line, which begins at 0 and ends at infinity in one direction. Normally called a ray, but you can see from this circle that the ray describes light and it also describes gravity. They're not defined on a line. They're defined on a ray, because a line always has a center. There is no line that goes in two directions. That's the
failure of bilinear extensibility. That it leads to the calculus, it leads to sine cosine, it leads to complexity, it leads to Dirac's double complexity, it leads to Albert Einstein's hypercalculus, and the sky's the limit now.
Is the line quantizable? The absolute verdict is yes. Well, that's where we get the quantum from, because now you have a quantum limit to your measurements, because you quantized a continuous object. Is the line continuous? I want you to think about that. Do you know what continuity is? Noether Bošković talked about this in his book Theoria Philosophiae Naturalis. He's certainly not alone. Leibniz studied the same thing. Of course, Newton did. Both of those men were essentially the forebears of Noether. Of course, he used the line for its typical purpose. Do you know what that is? It's the measure of distance, called linear spatial separation. In order to do that, the line must be quantized. But in order to quantize the line, to put numbers on it for distance, In order to quantize the line, you must use extrinsic geometry, a point. And a point, by definition, would have no existence. So those numbers are unreal. 1, 2, 3, 4 are not exactly numbers, because they're not related to anything except each other on a very simple metric, 1. The metric of the line is based on its index. That's the smallest unit of separation. You have to separate the points or they're not distinct. I think you see the problem. This is a problem that has torn the hair out of every mathematician who's ever gotten serious about numbers. Are numbers separate from each other? If they are, then they're quanta on the line. Because they're separate, well, how much space is between them? None? That's what Cantor tried to prove, is that there is no space between the quantization numbers. Those are extrinsic. They don't belong to the line. We're trying to match the numbers to the line. And Euclid showed that if you begin with 0, you can quantize the line for distance. That is so utterly elementary and simple that it's easily not seen. So I hope sincerely that I'm not daunting you, but I would expect that I'm challenging you. There are 2 ways to look at a number. And normally we think of a number as a position, but it can only be a position in relation to another point. And in our linear system, that's always 0. It has to be, because you have to have a place to start from to jump to 1. That's called the quantum linear jump, because it establishes the metric, which is what again? The metric is what you're measuring. It's linear spatial separation. Now that's the geometric term. It's separation. Separation of what? Now you're talking about relationships. So when you have distance, you must have a start. Otherwise, you don't have a definition of distance. Without a starting, we say point. But we use the Euclidean point. Well, that is non-existent geometrically. So that is a wild conundrum, because we know that distance works on the line. So it is a good match, but it leaves a hole at the end of the line. It leaves a hole at both ends of the line. And I want to look at that, but first, before we look at the wholeness of a line segment, that is a measurable distance, that's what the radius is a measurable distance. In the third chicken scratch that says circumference equals tau r, the circumference equals tau times the radius. If you want to instantiate a unit circle, which is, of course, always used. The unit circle is ubiquitous in physics. I used it for decades. I am simply showing you that there are 2 ways to parameterize this circle, because you can invert the relationship. Because here's the problem with the 2 numbers in the relationship. Tau is irrational. That has been so downplayed that it's remarkable to be able to say that we simply brush that under the rug, as it said. That number cannot be computed. It's an incomputable number. That means it's a non-representable number. Those 2 adjectives are strongly related. The preferred term is incomputable, but the more technical term is non-representable. That means non-machine representable. That means non-binary. Binary. Binary logic is what gives you your cell phone, your computer, and a lot of other things, is binary logic, because that's machine logic. Well, it is based on 0, 1. It's on, off, and one of those numbers has to be 0. So there's no getting rid of our natural number system. But you do need to characterize it now. It's a one-component number system because a distance is a one-component number. Virtually synonymous with a linear number. That is correct. A linear number, first of all, is a quantized position on a line, and a distance, which is the whole purpose of having that metric, is to get a linear separation in space so that you can measure a distance between two objects. That is the definition of the linear number system metric. It computes linear spatial separation on a one-component number, on a line. If you invert the circumference irrational value to put the fifth chicken scratch, I skipped the fourth. Let's go through this. If you take the circumference and try to relate it to the radius, the constant converter is tau on the radius. That gives you the circumference. Well, obviously that's a multiplicative relationship. It's the simplest of all equations. C equals tau r. Well, then move the tau underneath C on the other side. That's equivalent to dividing both sides by tau. That's considered a logical operation in mathematics, and a moment's thought should convince you of that. I'm sure you're already convinced of it, but I'm being thorough here because this is formal. Now you have a definition of the radius to make the radius a one-component number, which it should be because it's a line. So the radius should be the invert of tau on 1, because you want the circumference to be 1. When you set the radius to 1 over tau, you've put the irrational number where it belongs. It's on the irrational line. The line is purely irrational. Cantor came within an ace of proving that. But John Horton Conway, I believe it was in the late 1970s, was able to prove that there is a second number system that has been overlooked, which in his interesting formulation of the surreal numbers, named by Donald Knuth of Stanford, and now internationally famous and internationally overlooked, it's not overlookable what John discovered. He proved that the line is the number system, that's first. He proved for the first time in mathematic history what a number is. And it's identical with a point on a line. But when you say that, he was able to prove that by saying that, by quantizing the line with points, which must be separate, you have made an infinity of fractal infinities. And that's very hard to even conceptualize because infinity is already an imaginary concept in our minds because we can't conceptualize infinity. That's basically its definition. It's that which cannot be conceptualized either mathematically or geometrically. There's a loophole in that which I discovered. But it's due to John Horton Conway's work. So that's merely to say his most important discovery is not the definition of the number, although that had to come first. And what is his definition of the number? It is a quantization of the line. Any one of them is a single quantization of the line with an imaginary point. And when you do that, to infinitely densify the line with imaginary numbers, you get an infinity of fractal infinities, which is extremely difficult to conceptualize. That's the answer. That's where all irrational numbers originate, not on the circle. And so the circle cannot have an irrational parameterization. Euclid forced the circumference of the circle to tau. You can also say 2 pi. All right. So that's the complete sequence. What that proves is, that is what John Horton Conway actually proved, and apparently I'm the only man to have recognized this, is that the line, the straight line, the number system that we use, is congenitally quantized. That's where we get the concept of a quantum from, because the lowest number in the metric is called the index. That has to be 1. It doesn't matter what the scale is. It simply has to be 1, because that's the first number after 0. That's the correct answer to Georg Cantor and Dedekind and ultimately Riemann and everyone who followed. They didn't see, and that's a good pun, they didn't circumference-y. They didn't circumferize. They did not circumferencize 1. They never saw that 1 has to be a continuous number. Otherwise, you can't capture physical continuity. What do we have instead of physical continuity, which ruled science for thousands of years? We have a new idea. Physics is quantized. Is it? I proved that it can't be. And that's why you have a quantum paradox. It's because you're using one-component numbers to measure continuous space and continuous time. That would be, ultimately, as I've also proved, continuous energy. Energy is continuous. So it's not quantizable. Then why have we quantized it? Because we don't have the right number system to capture continuity. Well, what would that be? Is there such a thing? There certainly is. You're looking at it. C equals 1 is naive. It's a 2-component number, isn't it? Now here you have a simple circle in GeoGebra. That circle, I want you to now perceive, is the number 1. And to prove that, up in the upper left-hand corner, I should have this. This is a prototype. This will be, you'll see a lot more soon. But it says omega equals 1, and then below it says, again, omega equals 1. Omega is the circumference when it's unitized. So that's why I use omega instead of C. So since omega, that is that blue line that goes around in a circle, that is the number 1. Is that true? Yes, because it's linearizable. That's the magic of the number 1. That is the linear number 1. So you're looking at the quantum jump from something to 1. But it's not from 0 to 1. Unless you think of A, which should be labeled O, the center, is that 0? Yes. That point at the center of the circle is John Horton Conway's 0. And it actually has a name, and you can look this up in Wikipedia. I haven't done a full study on this, but I was amazed to learn that 0 is now given a new designator in mathematics. In a certain context, I'll put it that way for the mathematician's protection, in a certain context, that 0, which is at the center of a circle, is a double 0. It's a 2-component 0. John Horton Conway proved that that's true. That's his axiomatic basis. That's the re-basis of Euclidean to non-Euclidean. Because now we have a redefinition of the point. It can't be 0. It can't be null. It has to be double null. It's double null on a 2-componency. It's a relationship between nothing and nothing. And if you think about it, that's the relationship between x and y at the origin, is the relationship of nothing in one direction to nothing in an orthogonal direction. That's a double 0. And those two zeros are perpendicular in imaginary space. That's going ahead of the game, but I want to tantalize you. This goes all the way. So when you say that omega equals 1, you're talking about the circumference. Omega equals circumference. But the circumference would be the unit circle, which puts tau on the circle. But when you invert it, as we just did, omega is the circumference, and that 1 is a linearized 1. What should it be? It's a two-component number. You could say it in many ways. 1 is a most extraordinary number. It's transdimensional in both dimensional systems, both sphericity and in linear formulation. The number 1 multiplies to itself and it divides to itself. That's extraordinary because that's closure in multiplicative space on unity. Well, that's the multiplicative identity. So the multiplicative identity is on the surface and the additive identity is at the center. I want to repeat that and close this off as we went to a half an hour. The center, labeled here A, is the additive identity on 0, 0. The surface, which is a surface, not a point, has a value of 1 proportion 1 in circular space. And that's nonEuclidean. And that's a new number system based on 2 componency instead of 1 componency. Correct? I know this is a lot, but we have to close this off because I've gone 35 minutes. Stay tuned. We'll have a lot more. I hope you're having a good time. I know that I am. This is the transition of physics and science to the 21st century due to the discoveries made in the 20th century, which apparently I'm the only man to be able to synthesize in order to make sense out of our fundamental discoveries in astrophysics and quantum physics. Stay tuned to Anagalactic, your source for the secrets of the universe. We'll be right back. Keep looking up, okay? We'll be back today, December